Pynq is an open source project from Xilinx that makes it easy to design embedded systems with Xilinx system on chips. Using the Python libraries, designers can exploit the benefits of programmable logic and microprocessors in Pynq to build high-performance embedded applications with parallel hardware execution and low latency control. The goal of the project was to implement spiking neural networks on FPGA to improve their performance. SNNs are artificial neural network models that closely mimic natural systems. The idea is that neurons in the SNN do not fire at each propagation cycle, but rather fire only when a membrane potential and intrinsic quality of the neuron reaches a specific value. When a neuron fires, it generates a signal which travels to the other neuron, which in turn increases or decreases the potential in accordance with the signals. Now let us see how the flow actually works. The images of size 28 cross 28 from the analyzed dataset are sent through an encoder to generate the spike trend for the respective pixels. We give this spike trend as input to the network, which then classifies the labels accordingly. The network part here is the most compute intensive one and needs to be ported on to FPGA for added performance. Going on to the overall flow we have followed, the SNN models have been implemented in Python and we have trained the network using HTTP protocol. Once the training was done on a sufficiently large dataset, we have collected the bit matrix generated and used them in our hardware implementation later. Also, the performance measurements were done to calculate the error rate of the implemented architecture. We have then migrated the implemented one to C++ for high-level synthesis. The HLS has been done to generate the Verilog files, which was then ported on to the FPGA Pynq port for hardware acceleration.
We implemented a clear SNN network that is able to detect first 6 digits successfully and ran it on an Intel i7 core found in standard laptops. A handwritten image of digit 3 from the MS database was fed as input to the network. Each pixel value in this image was then converted to a corresponding spike train of 100 time steps. A small snippet of the produced spike trains can be seen, wherein a higher pixel value corresponds to a higher frequency spike train. We then designed the architecture of the two-layer network with 784 input neurons and 8 output neurons. The weights were obtained by the extensive training and parameter tuning of this network to attain an accuracy of 96%. Based on the incoming spikes, the potential of individual neurons were updated, and whenever an output neuron crossed the predefined threshold potential, the neuron was set to spike. The total spikes of each of the output neurons were then evaluated to determine the class identified by the network. For the current case, the maximum spikes were obtained for the fourth neuron, which corresponds to the digit 3 as is expected. The time taken by the network to make this inference was estimated to be 0.19 seconds. Similarly, we can see a successful classification for another input image of the digit 5, and the execution time is found to be consistent throughout at 0.19 seconds. We ported the Python implementation of the two-layer SNN network onto the Pynq board and ran it on the on-chip ARM Cortex A9 processor to benchmark the performance in standard embedded system platforms. The same handwritten image of digit 3 was fed as input to the network. As expected, the network successfully classified the input image, but there was an almost 17x decrease in overall performance as compared to the execution on the Intel core. The inference process took an average of 3.2 seconds in the ARM processor, confirming our intuition that the performance was poorer on standard embedded platforms. We succeeded in developing a working baseline implementation of the two-layer network on the FPGA, along with a DMA unit to facilitate data transfer. The generated bitstream was burnt onto the board. The DMA module was responsible for sending the input spike train to the programmable logic and consequently collecting the output spikes. The overall processing time, including the communication overhead, was found to be around 0.09 seconds, which was almost 40 times faster than the ARM implementation and 2 times faster than our laptops. To attain great accuracy and complete 10-class classification, we shifted to a more complex 3-layer SNN architecture having a hidden layer of 64 neurons and 10 output neurons, which was ported onto the FPGA. Due to the added complexities, the overall execution time for the baseline implementation was around 0.19 seconds. That is, it increased by a factor of almost 2. The performance, however, was still better than the nominal software implementation on an ARM processor while giving more accurate results. Ultimately, it's a trade off between accuracy and performance. In conclusion, the 2 and 3 layer SNN architecture has been implemented on the Pynq board and a performance improvement of 7x has been achieved.